Welcome to the GR lecture this late afternoon. I have last time introduced two new notions, namely the notion of torsion and the notion of curvature. And these are the notions that I would also like to discuss a bit in more detail today. I think I just gave you the definition last time. These are notions that will again make our connection to physics a bit more concrete, because these are like the covariant derivative, things that you can determine in principle by a direct experiment. And the experiment consists of moving gyroscope around in space and compare their directions. But let me start with the mathematical part of this and remind you briefly of the definition of torsion. That's the chapter 3.12. I'm aware that at the end of last lecture, I had two chapters in one, torsion and curvature, but I only gave the definition. Now I will discuss these in more detail. That's why I now call or name these sections separately. The torsion was defined already, but I briefly write down the definition again so that we can use it today. So it's actually a covariant derivative, or a difference between covariant derivatives, and it also involves a Lie bracket. I hope you have seen that or remember that. Now, what do we need to do first? The thing that we should first verify is that the object defined here is indeed actually a tensor. Now, what does that mean? A tensor should be such that if I change something in one of the arguments, so for example, take this x argument here, this is a vector field. So it's something defined all over the manifold, all over space-time, if you like. If I change here something at a certain point in the manifold, this should only have an effect at that point also of the resulting tensor. So in other words, or more mathematically speaking, what you want to test is so-called C infinity linearity, or C infinity M linearity. Maybe I should separate the kind of physical meaning of that and the mathematical meaning. If you just think mathematically of it, then what it means is that you take a function in C infinity M. So it's a function that assigns to every point of the space-time of the manifold M a number. And now you ask the question whether if you, for example, multiply one of the arguments, and I just take here the second to illustrate that with this function, is it the case that I could just equally well multiply the tensor with the same function? So maybe to see the meaning of that, it is useful to remember that everything is defined on the whole manifold. So what this means, if I multiply the tensor with f, means that if I look at it, if I evaluate this entire tensor, so the entire product here at a certain point P, then what I do, so let's do that. Maybe I want to evaluate both sides at P. So I put this little dash here, P. What this means is that it's f at P and then T phi x y evaluated at P. So that's what how the product is defined on functions of the manifold. So this can only be true. So you see on the right-hand side of this expression, of this whole equality, I just have a factor f of P, which means that if I evaluate this thing here on the left-hand side, only at P, then only the P part of this argument is relevant. So in other words, what I put here into the tensor, if I change this at a point different from P, then nothing will change if I evaluate at the end the result at P. And that's really a locality property that needs to hold. And only if that is true, we speak of a tensor. So a tensor has to satisfy this infinity linearity. So in other words, if we say that this is a tensor, we need to verify that. And we need to verify that for all the arguments separately in principle. So let's do that. So actually in the first argument here, it's kind of almost obvious. So imagine I multiply the first argument with a function f, and then I write out the definition, then I just have f times this. So I will not even write this. It's clear that if I put an f here at this spot, this will just land here. So and then I can of course take it out. So I clearly have f infinity linearity in the first argument. Now in the second argument, it means exactly what I've written here without the blue part. So that's what we want to prove. So let me do a little proof of that. So maybe I'll just, how should I? Okay, I think I'll just do it in the second argument, and then I will say in words how we proceed with the other arguments. But maybe you see already now that if I prove this in the second argument, I don't need a separate proof of the third one, because the whole definition here is actually symmetric, more precisely anti-symmetric in the second and third argument. So if I exchange these two, I just get minus the t of x and y. And therefore, if I establish this f linearity here in x, I immediately can conclude that it must also hold in y. So we only need to do the work once. But let's do that work. So to establish that, there's indeed a little calculation that we need to carry out. Okay, so let me just start by writing down the left-hand side of the equality that we want to prove, which is this one. And now I just write it out. So I insert it into the definition of what a torsion means. And so whenever I have an x is now an f of x. So the whole thing looks like this. Let's now consider the individual terms. This term here is actually quite easy to rewrite because we already know that the covariant derivative is the infinity linear in the argument down here. It's not the infinity in this argument, but in that one here. I mean, that's something we already established. That's essentially true by definition almost of the covariant derivative. So we can immediately write that this term is equal to this. Now the next term is a little bit more involved because here, as I said, the second argument is not C infinity linear in nabla. So more precisely, we have to actually apply the chain rule. So we take the derivative first of f and multiply the whole thing, then with x, plus we don't apply to f, but instead apply the covariant derivative to x. That's what the chain rule says. We have already seen that the covariant derivative satisfies the chain rule. So I just applied that one. And then here, that's the Lie bracket. And I think you should, in the meantime, after you have done the exercise classes, be a little bit familiar with the Lie bracket. And you have probably seen, and otherwise you can easily verify that, I will not show it now, that the Lie bracket is also not C infinity linear, but you have a term as if it was. But then you have an additional correction term. I think I've even shown it in one of the earlier lectures, which looks like this. So that's something you should already know. And now we are almost done, because if you now look at this expansion that I wrote down, there are certain terms that cancel. Namely, this term here, which appears in total with a plus, because there's a minus here and a minus here, is actually just the inverse of the term here, which appears with a minus. Because remember, the covariant derivative here applied to a function is the same as just y of f. So what I encircle here is just this thing here. So therefore, these two terms here cancel, and what we are left with is just what we actually want. Namely, we have an f in front. Clearly, the phi itself is a linear function. That's itself a covector field, and the covector field is, again, of course, a tensor. It's a 1, 0 tensor. So if we put a function inside this f that would be here now, this can just be drawn out. So what we obtain after all these manipulations is essentially almost directly what we actually desire to have, namely this, which is of course f of t phi x y. And that concludes the proof. So we have established that indeed the torsion is the infinity linear. I've shown it for this argument here. I've argued that this also means that it's the infinity linear here. And I've also said that it's trivial that it's the infinity linear in the first argument, because that the f then directly occurs here in the outside of the map. So with that, we have verified that T is indeed a tensor. So let me just remind you that therefore C infinity linearity is actually an important thing to verify, and it's not usually given. We have just seen the example. The nabla, for example, as we have just seen in the derivation, is not C infinity linear in the second argument. By the way, what does this mean intuitively? It means that if I change here the argument y at a certain point by multiplying it, for example, with a function, then the result of this depends not only at the change at that point. And that's very clear, because this thing is like a derivative. And if you take the derivative of something at a certain point, then of course it's not only this something, this y here. What is relevant for the derivative is not only the y at the point, but also the y in the neighborhood of the point. Because if you only know y at the point, you don't know, for example, how steep the curve is there, or what, and therefore could not calculate the derivative. So a derivative is a typical example of something which is not a tensor in that sense, because it not only depends on the point, but on the neighborhood. However, in the exercises, you have seen that it's still a local quantity in the or a local evaluation, in the sense that the derivative only depends on the neighborhood and not on stuff far away. So it's sufficient to know how, if you want to know what this is at the point P, it's sufficient to know what y is in an arbitrarily small neighborhood of P, but it's not sufficient, because it's not the infinity linear, this thing here, it's not the infinity linear, to only know y in 1P. However, for this thing here, if you want to know what this is at a certain point P, it's sufficient to know all these inputs here only at the point P. And that's what this thing here means. So we have established that. Now we also, from that, see that it's by far not obvious that an object that you define in a apparently complicated way by adding and subtracting covariant derivatives is at the end still a tensor, because things indeed have to cancel. So the individual terms would not be tensors, and only the combination, including the Lie bracket here, makes it a tensor. So see, if I dropped here the Lie bracket, we would not have this term, and this term would therefore not cancel, and the whole thing was not a tensor. So that's in a way the explanation why we need the Lie bracket here. Of course, there will be other explanations, but this is maybe just the explanation which would say that if you would just define this only as your tensor, it would not be a valid tensor, because it would fail the proof we just made. Okay, are there questions up to this point? Okay, don't see any. By the way, first of all, I would like to thank all those who actually gave me feedback by email and so on. To the course, this is extremely useful for me to adapt the course to your needs. please continue to ask questions. I really appreciate this still, even though the course is now progressed and I've kind of probably adapted to a certain, or I've assumed a certain speed. I can still change things if there is a need to do so. So please feel free to comment and in particular to ask. Because if you have a question, you are very likely not the only person who has that question. Now for completeness, and this is something you can certainly or should be able now to do yourself, but because it's something we will use later, I'll just do it to make sure we all have it in our books. I want to express this tensor in terms of coordinates. Okay, now for some reason my computer tells me that it will turn off in 5 minutes. I have to do something. Okay, now it's okay. I will stay. So that we have to express the tensors in components. If you remember what that means, that's actually a nice thing in a way, is that we just can ask the tensor what its components are by giving it as input the basis element of the basis and the basis of the co-basis or the dual basis, if you like. And of course, the basis we are using is the coordinate induced basis, and that's exactly what I've written down here. That's always the same trick. That's a generic way to get a coordinate. And by the way, this also makes clear that a coordinate an actual coefficient here is indeed a coordinate-dependent thing, because you have here the coordinate-independent tensor, but then you feed it with the basis. That's just a reminder. So let's evaluate this. To evaluate this, what we have to do is just to apply the definition. The definition says take first the covector that is the first argument, which was called phi before, then take the covariant derivative along the direction of the second argument, which is d to the dxj, that's a vector. And the thing you have to take the derivative of is the third argument. And then we do the same thing in the opposite order. So we take it along k and take the derivative of d to the dxj. And now I stop here. I don't write the Lie bracket. Why don't I write the Lie bracket? Because we have already established that the Lie bracket between coordinate-induced vector fields, dxj and dxk, always vanishes. That's something we did some time ago, and I hope I told you at that time that that this is an important fact that will be useful. And here it's one of the places where it's indeed extremely useful, because we don't simply need to care about this Lie bracket, which simplifies things a lot. It simplifies things so much that we can immediately write down the solution, so to speak, because we know already, that's something we also established last time, that if we take such an object here, the covariant derivative in a direction dxj of a vector field d to the dxk, and take the i's component, that's exactly the gamma symbol. So we have here gamma I k j. Okay, now, yes, I think the convention is that the direction is always the last argument of the gammas. And so the second gamma function comes from this term here. Here we have it in the opposite order, gamma I j k. That's it. I can just write it using the notation of the antisymmetrization bracket in the notation. And then it looks like this, kj. So this little bracket here means exactly that you once write down the term in the order kj, and then in the opposite order with the minus sign, and divide by the number of terms. But because I don't want to have this division, I have to multiply again with 2 to end up with this. So that's something you should already have seen more or less in the exercises. Now, I think I don't want to say much more about the torsion so far. I will later come back to it and will try to give you kind of a geometric interpretation of what it means. I'm aware of the fact that I haven't done so. I just told you this is an object that somehow depends on the parallel transport, because it depends on the covariant derivative. But what you should keep in mind is that this object defined here is something you could in principle determine experimentally, as I said at the beginning. So this thing is in some way, you could go to an experimentalist and ask him, please determine this tensor here. And what this experimentalist would do is he has to first of all, I mean, he could think, of course, an experimentalist needs at the end to write down numbers. So the best way to do that is to go to coordinates. He probably chooses a coordinate system. So he maps out space-time with a coordinate system so that every point in space-time has a well-defined name, so to speak. And then what he has to do is to essentially determine these gamma symbols. But these gamma symbols, if you remember how they were defined really in an experimental way, namely by how a gyroscope changes its direction if you move it along a certain path. So more precisely, you have to take a gyroscope that points in the J direction, move it along a path in the K direction, and check how its I component changed. And that's essentially this thing. So that's really something that is completely determined by experiments. In other words, and because, I mean, once we have the components, clearly the tensor itself is determined because we have it then for all the basis elements and everything else follows by linear combination. So this is really an experimental quantity, and we can now ask, how is it in nature? How is this quantity behaving if we are now taking space-time not as an abstract space-time, but as the space-time that is really physically there, our four-dimensional space-time out there? And what we find, or what we would find, or did find probably, is that the torsion is always zero. And that's now something we, as a theorist, just put as a postulate. I put it as the postulate because of, I guess, at the times when Einstein developed the theory, he didn't do such experiments, but he still somehow had the right intuition. And so the postulate in GR is now that space-time is torsion-free. So, because that's an important postulate, I just write down the obvious implication. It means that whenever we have such a combination of two derivatives, of two covariant derivatives, we can replace them by the Lie bracket. I mean, that's obviously a consequence of torsion being equal to zero. Or in coordinates, again, or if we introduce coordinates and write things down concretely, what it means is that the gamma symbols are symmetric. So I can again write this in a nice notation, namely using the round bracket. The round bracket has the same meaning as the square ones, except that it's the symmetric and not the antisymmetric permutation. So I just add the terms up with the different order and divide by the number of terms. And so what this thing means is just if I interchange J and K, nothing changes. And that's, of course, what is implied by saying that the antisymmetric part is zero. So now we have incorporated another fact about space-time. So remember, we did that in sequential order. We started with an almost meaningless thing. Apparently, we just said space-time is a set of events, namely, I mean, event was a basic notion. So space-time is just the set of those, and you can think of an event as, for example, a light bulb flashing or so, something happening at a particular point in time, but time is not yet defined. It's just an event. That's the basic notion. We took the set of all those, then we equipped it with a topological structure, saying what are close events, and now, and later with a differentiable structure. And then we said, oh, now we want to have an additional element. We want to talk about directions changing. And we did that by saying a differential manifold, and therefore space-time can have an affine connection. But an affine connection can be arbitrary, but now we are saying something about it. Now comes in again a physics set. By saying that there's an affine connection, we didn't do much because we just said there is one, but we didn't specify what properties it has. But now we said it has a very specific property. It's a torsion-free connection. And that's clearly a physics ingredient that you cannot justify mathematically. You can maybe do it by the beauty of the theory and say it's more beautiful if the torsion disappears and so on. But ultimately, this is a physical fact that is that may have a deeper justification, but in GR, it goes in as a postulate. Now, the other tensor is the curvature, which we also defined already. It's a more complicated object with 3 components, and I'll write it down like again for you because it's also a central object, so it's probably worth writing it down more than once, and especially when you use it. So it's this thing here. By the way, generally you should think of both curvature and torsion as, some people say, tensorial information about the connection. So these lambdas that appeared at the beginning were clearly depending on a coordinate system. If you go back and look at the definition, we immediately from the start introduced the coordinate system and said an affine connection is defined by a structure that has some parallel transport, which in certain coordinates has the particular form expressed by these lambdas. But now these lambdas are not very satisfactory, of course, because obviously they are somehow dependent on this choice of chart. But now we want to extract something that is physically there without us defining a chart. And the torsion is such a thing. And saying that the torsion is 0 therefore makes sense. It wouldn't make sense to say that the gammas are 0, because the gammas really depend on the chart. But the torsion is a tensor, and the tensor is not depending on a chart. And so saying the torsion is 0 makes sense. And for the same reason, it's useful to talk about the curvature, because it will again be an object talking about which makes sense without first defining a chart. And indeed, as I already announced, the Einstein field equation, which are the main equations determining the structure of space-time, will tell us what this curvature is. They will give us information about this curvature. Actually, not about this object itself, but about the contraction of this object, as we will see. So again, we have to do some work. Namely, we have to do, again, prove the C infinity. Maybe I write it as a claim. We have to prove the C infinity linearity of this object that I just defined, and therefore prove that it's a tensor. So R is C infinity M linear in all arguments. Now I'm actually not sure whether I should really do this calculation, because it's a quite, okay, it's not so tedious, but it will take some time. The calculation is very similar to the calculation I've already done here for the torsion. It's just that writing the definition out and using the usual rules that we know already for the covariant derivative, and then canceling terms and observing that it's indeed C infinity linear. Okay, so should I do it? Maybe I'll just ask you. So if you want me to do it, press yes. And if you don't want me to do it, then proceed with the next topic, then please vote no. Okay, there's a, okay, it's getting tight. So don't, okay. Yeah, it's almost equal. Now I think the yes has won. Okay, I guess it's probably okay if let me do a compromise, as we usually do. I think in politics in Switzerland, when a voting comes out like that with an undefined result, let me do it for one of the arguments. And okay, actually, yeah, let me just do it for the first one, if you don't mind. So, I mean, not for the first. The first is trivial. The second one for a second. So, Let me write this down. First argument. This is again obvious. Or I write down trivial for the same reason as it was trivial for the torsion. Because the phi just already appears outside of the bracket, and clearly if I multiply this with a function f, the function f is just outside. I mean, it's essentially just obvious from the definition. That's what I mean here from right, trivial. In the second argument, we have to do it. And yeah, okay, maybe it's actually better if I show it for the third argument, because it will have a larger effect. The third argument will also, if I prove it in the third, it will also prove it in the fourth, because again, we have a symmetry between the third and fourth. So in some way, I'm more efficient when I do something for the third one, because I will immediately prove it for two. So let me therefore write for the second one, see lecture notes. So the proof is there. And for the third argument, I do it. And you can ask, of course, questions if anything is unclear here. So what we need to do is again to multiply the third argument with a function f. Again, I will not write this, but f is again some arbitrary c infinity function on the manifold. Okay, I will probably need more space, so let me here allow some space to summarize terms. So the first step is always to just write down the thing more or less, but already do some trivial things that I can immediately do. And I already told you before that in this argument here, we have anyway C infinity linearity. So rather than writing nabla fx, I can immediately write f nabla x. And then the second derivative is according to y. There is no f there, so that's this. Then the second argument is, or the second term is probably more interesting, because now I take the f out of the nabla as before, but now it's still in the covariant derivative of y, so this will require some work. And then we will have the third term, which is the Lie bracket here of, and here I just take the f out of the Lie bracket already. But of course, I know that I'm not allowed to do that. So the Lie bracket is not C infinity linear. So I have to put an additional term. And it's the same. So what I'm doing here is I use the same thing as here. So we know that if I have a Lie bracket, like you see here in the previous note, in the function there, that I can draw the function out. So that corresponds to this thing that I just wrote here. But now I have this additional term with a minus. So what does this mean? Because I anyway had a minus, I get again a plus. And then I have a derivative to the yf applied to x and the whole thing to z. So that's essentially the derivative that comes from this term here that is thrown out of the Lie bracket. Okay, so far I've already done a bit of work. So I have not only written down the definition, I've already tried to take out f in the first order, so to speak. Now let's do the next step. If I look at the first term here, there's nothing to do here because f is almost already at the outside. And as before, taking the f out of phi is immediately allowed because phi is already a tensor and therefore C infinity M linear. So I can always take functions out. So let's just keep this term as it is. Here, however, I have to apply a product rule because the derivative to the y in direction y acts on f times another vector here. So let's do that. So this whole term here is first of all the derivative applied to f only, and then the derivative of x in the direction of x of z. But then the second part of the chain rule tells me don't apply the derivative to f, but apply to the second part. And the second part consists of a derivative of x of z. Okay, so that took care of the second term. Let's look at the third term. I think this is again now easy because we know now very well that the covariant derivative is C infinity linear in the direction argument. So I get something like this. Here, I can just take out the f. And for the last term, okay, let's see. Yeah, I think we can do the same. Y applied to f is again a function. So remember, a vector applied to a function corresponds to the derivative of the vector of the function in the direction of the vector, which is again a function. So that's a function, so we can take it out of the nabla and just write it like this. Then we have nabla x of z. Okay, so let's see whether some terms cancel here. I think, okay, let's see. Where are terms that cancel? Oh, yes. So maybe something I didn't write, but could write is here that a nabla y applied to f is again the same as y applied to f. So remember, the covariant derivative applied to a function is the same as just the vector applied to the function. That was part even of the definition of the covariant derivative. You can just look it up there. And that's indeed important to do because now we have here yf times nabla xz, which is exactly this term here. But it appears first with a minus sign and the second time with a plus sign. So these two red boxes cancel. And now I'm almost done because if I write down things without the red boxes, or if you just look what remains, then we have, first of all, here a term that corresponds to the first. So what remains are these green terms. And if you look at the green terms, they correspond essentially just again to the definition of the curvature with the f in front of it. So I just still have to take the f out of the bracket, but I already argued that this is possible. So indeed, what we get is here f of r phi z xy. So I did it this last step a bit fast, but I hope you can, when you have a quiet minute, just sit down and see that I indeed didn't forget any terms and that this last equality is justified. But please interrupt me if you're not convinced by that. Now the fourth argument. So see linearity in the fourth argument. We have already done the third. Is follows by symmetry, as I said before. So the x and the y argument are symmetric. By the way, the reason why I called the second argument z and the third x and the fourth y is in a way has to do with the symmetry, that we have symmetry between x and y, which is the same symmetry that we have already here when you look at the torsion. And so it's kind of easier to remember if you use these type of labelings. But that's just a convention. So you shouldn't search for a 2D meaning of this convention. Okay, I hope that's now clear. I could now, yeah, I hope it's okay also now to go with this compromise that for the second argument, it would be again a similar calculation. It would probably be similarly long. But I don't think it will involve any new elements. It's still the same rules that I now used that appear in there. There's no other rule or other trick that you have to use for that. The good thing is you can all read up in the lecture notes. Now again, I want to write down the whole thing in coordinates. And so we have to play this game again of saying, how do we extract from a tensor the components? That's very easy. We feed it again just with the basis vectors. So let's do that. Let's feed that tensor. And I call them here, the last one dxm and d to the dxn. Oh, I just noted that this m is not very readable. So let me write it again. So that's it. Now we can actually write this out. And one would maybe hesitate to do so because the curvature has a long expression, but again, we can profit from the fact that if we use a coordinate-induced basis, the Lie bracket just disappears. So we can immediately forget about the last term in the definition, which you see here. So the definition simplifies just, or the terms we have to take care of are only the first two. And these are now specifically the ones I write down. So first of all, we take a derivative in the direction of m, and then a derivative in the direction of n, of the n coordinate, of the vector d to the dx chain. And then we have also the second argument, okay, that will be with a minus. And here it's just the order that is the opposite one from before. And everything else stays the same. Let me nevertheless write it for completeness. I could just have used the anti-symmetrization bracket, but this is a bit ugly here, so I will not do it because I wouldn't know where to start the bracket and where to end it. So let me do it like that. Now let's evaluate this. And to evaluate this, it's again useful to remember that we can write expressions like these, like this nabla here, in terms of the gamma symbols. For that, I need a bit more space here. So let me here make some space. Okay. Now, what are exactly the what's the gamma symbol notation for that thing? You can easily see that, I mean, now I don't have a dx in front of this term, but I can just introduce a new index, let's say R. That's an index over which I will sum. And then, according to the definition, this is gamma j n. And then I multiply it with the vector d to the dx r. So that's essentially equivalent to what I did before. This is just saying that the rth component of this vector here is given by this gamma symbol. And of course, then the whole vector is given by the sum of these components times the basis vectors. And the same I can do for the lower term here, for that one, which is therefore, I use the same summation index because the sum anyway ends beforehand. And it's this time jn to the d to the dxr. Okay. Now the next step is to evaluate the nabla acting. So here there's still a derivative acting on this gamma symbol. And that's here a bit more complicated because we have here a product, namely the gamma symbol itself times the basis vector. And you know that the covariant derivative of a basis vector is again producing a gamma symbol. So we will actually get squares of gamma symbols. And this will lead to the following expression. So let me maybe, okay. Yeah, so the simplest way maybe to do that is to use some color coding. So let's do this, or okay, maybe a larger box. So I now apply the derivative to this whole thing here, and I write everything that comes out of that in green. So what is it? According to the chain rule, I first apply the derivative to the gamma symbol, which is a scalar. And you know that the derivative applied to a scalar, a covariant derivative applied to the scalar is just the partial derivative. That's something we have already seen, which can be written with a comma. So the first term, in other words, is gamma rjn, and then derived in the mth direction. This is what this comma here means. And then we still have the second term d to the dxr, which is not, on which the derivative doesn't act in this product, in the first term of the product rule, and then we have to act on that one. So we don't act on the lambda symbol, on the gamma symbol that is already there. So I just write it down. But now we have to act on this thing. But here we already know that, as I said before, this produces a new gamma symbol, namely a gamma symbol, which again has a new counting index S. Then it's taking the derivative of a vector in direction r. So I write as a first index r, and then in the direction m, that's the direction in which the derivative goes, and the whole thing has to be expanded over these vectors S. So that's the same trick as above. It's not a trick, I just write out the vector as a summation over the coefficients times the basis vectors. Now, exactly the same thing has to be done for the other term. So I have to do this thing, and let me write this down. Here everything has a minus. So first of all, the product rule applied to the gamma symbol gives rjm comma n, and then still I have the vector d to the dxr, and then for the second term again I keep the gamma symbol, but have the second term where I have to introduce a new variable s. Now I take the derivative of something into again the direction r, or of a vector d to the dxr in the direction of n. So this n here, and I have to use, this appears now here. And then again multiply with the basis vectors to dxs. Now we're almost done, and then we can make a break. So actually I forgot something. You remember, I had also this dxi in front. So I should always still write the d to the dxi. And also in the second term, it's a dxi with a minus. If I put here a minus, I should have here a plus. Okay, so I shouldn't have forgotten about those. But now these are actually useful, these dxi's, because what does the dxi do if it acts on a vector? It just gives a delta function. So this dxi with this thing just gives dx delta ir, or in other words, it allows me to replace all the r's by an I. So I can therefore just copy the green thing, replacing r by an I, which gives me I, j, n, comma, m. And now, just for convenience for later, I will now not continue with this term, but with that one. And here, of course, I have something very similar. I have gamma I, j, m, comma, n. And now I write down the other terms. So let's proceed with this one. Again, the r is turned into an I. So I have gamma I r m. Okay, now I need. Oh no, here it's different. Sorry, that was a mistake. Here, for this term, it's not the r that collapses with this I, because there's no vector r, but the s. So in this particular case, the s turns into an I. So what I get here is gamma, and let me first write the second gamma one, so it's the IRM, and then gamma RJN. Now I take care of this one as the next thing that appears with a minus. So the S turns into an I, Rn, and then again gamma RJM. Now I will, as I did in the past, put a red box around an expression, which means this is again something you should try to remember. I know this is a more complicated expression, but maybe you should, if you had at the end, let's say, a summary of everything that is really important to do calculation, that's definitely a formula that should appear on your summary. So that's the expression of the curvature, of the Riemann curvature, in terms of the gamma symbols. And you see, it involves derivatives of the gamma symbols as well as products and sums of gamma symbols. So here there's a summation over R. But what we really see again, of course, that's now not new, but what we see again is that the curvature is completely determined by the gamma symbols and therefore by the connection. So this parallel transport we defined before, which is physically motivated, determines the curvature. Or physically speaking, if we can do this gyroscope experiment to determine the gamma symbols, then we can completely determine in principle the curvature. Of course, we need to then do a very involved experiment with gyroscopes in all directions, also considering derivatives of what we get and so on. But if you can do all that, we can really get the whole structure, both both tensorial quantities, namely the curvature quantity and the torsion quantity. And here, that's the other insight from general relativity, we see physically that these terms are not zero. So in contrast to the torsion, the curvature is non-zero. And that's, of course, the whole point of GR, or maybe not the whole point, but an important point of GR, that space-time is curved. And what it means is really that the tensorial quantity, not the gamma symbol, something that is independent of the choice of coordinates, is non-trivial. If the gamma symbols are not zero, that doesn't necessarily tell you that the curvature is zero, and could just come from a strange choice or maybe natural choice, but or some choice of coordinate system that makes these gamma symbols non-zero. But the curvature being non-zero is something that is independent of your coordinate choice. It really means something. Okay, that's now a good point for a break. So let's make the break here at this time, and maybe let's continue at 5:05 again. I will, of course, as usual, stay in the break, and I'm very happy to take questions. There's now an echo.
Sorry.
Maybe. Okay, I guess there was a question, but there was a technical difficulty. Vixina, was there anything in the chat about that?
No, actually, she.
Okay, I'm here now.
Ah, good. Okay, now we can hear you.
Basically, I was just wondering, why did you do the only like the comma sign? Shouldn't it be like a semicolon thing on the first gamma, the first two gamma expressions?
This one.
Because gamma isn't a scalar, right? Like, yeah, exactly this one, yeah.
Okay, so you're referring to these things, and now what is it? Okay, maybe I misunderstood or didn't fully understand the question, but you're asking something about these two, aren't you?
Yes, exactly.
Mm-hmm.
So, like a little bit further up, we said we were gonna do the derivative.
Yes, right. Aha. So okay, now I think
I'm being a scalar, but they're not, right?
Aha. No. Okay. That's a good question, and I think there is the notation one has to get used to. Indeed, the gammas with the this gamma with R and J and N is really a scalar because it's really the component. It's a bit like if I talk here about R, the R is actually a tensor. So if I take the derivative of R, I couldn't do it in that simple way. But if I did take the derivative of R, I, J, M, N, that thing is again a scalar because it's R evaluated at all these positions. So that's just the real number. And that's the same for the gammas. So these things are really real numbers.
Okay, good. Thanks.
Okay, you're welcome. But thanks for the question. That is probably something that could have been unclear to many. But then I, just as an addition to that, once I know it's a real number, I can really treat it like a function. And we know that if I take the covariant derivative of a function, then it's just like the normal derivative in this direction. So it's again the rule that a covariant derivative of a function is just the vector here applied to the function, but the vector applied to the function. This particular vector, d to the dxm applied to the function, corresponds then, of course, to the partial derivative if we evaluate it. So that's the reason why I could put here then a comma, which is the abbreviation in our notation for a partial derivative in that sense.
So there is one question in chat, like
Yes.
R and T are tensors or tensors field?
Okay, let me just briefly open the chat because then it's easier to. Okay, yes, so R and S, okay, probably always set tensors. But in fact, we are now always, whenever let's say I'm defining something on the manifold, I actually mean tensor field. So I should probably always have set tensor fields to be correct. But I will in the future probably still often use this abbreviation tensors. But the answer is clear. Yes, R is a tensor field. It's defined everywhere in space, time, or everywhere on the manifold. And that was also the reason why we had to take care of this C infinity M linearity. Because if it was only a tensor at one point on the manifold, then it wouldn't even make sense for it to be C infinity linear. But thanks for making me aware of that. So I think I just in my wording, I wasn't careful enough. So take my statements about tensors as always statements about tensor fields. We are now always taking about tensor fields. And if you're not, I will make you aware of that.
Can I ask a question about like the physical meaning of the gamma symbols?
Mm-hmm. Yes. So is that your question, or you wanted to have?
No, it's not the question already. So
yeah.
It's about the gyroscope experiment and how to think about that in space-time, because in 3D space and also I'd say on a 2D manifold, I can imagine like a gyroscope as we know it can be used to determine a parallel transport.
Yes.
But if we include fourth, like a time dimension, how should I think about a gyroscope in that way?
Yes. Okay. That's really a very good question. And I think I will only fully answer it later once we have also treated space-time a bit even more physically. But to give you already now an answer, so there are actually several concerns. So the first is a gyroscope is, of course, only something that a priori has three directions in space. And so the question is, what is its time direction? So that's the part of the thing we will have to wait a bit until we understand kind of angular momentum in space-time. But indeed, there will be a natural way to regard these things like a gyroscope also as a vector in four-dimensional space-time. In the same way as we will actually see also momentum as a four-dimensional thing. We would also say our momentum is just something in space, but we will add a zeroth component. And we will also see that it makes sense to add, so to speak, a zeroth component to the angular momentum. But as I said, that's a part we will have to discuss later in more detail. Just you can, however, just think of it like look at already the spatial components, and with them you can already do the experiments. Actually, you can already do all the experiments when you exploit certain symmetries that we have. I mean, for example, let's suppose if you want to determine the curvature and you already know that the torsion is zero. That doesn't work for the torsion, but let's suppose you already know the torsion is zero. Then you already have a symmetry between the two lower indices of the gamma symbols. And if you have this symmetry, you don't need to prepare anything in the zero direction because you can instead just move it into the zero direction, which means that's the time direction. Now there's another difficulty. Of course, I cannot somehow, for example, do a loop in space-time. And I probably explained that in the example, at least, that I've taken, we take two paths or make a loop somehow on the Earth's surface. But that can be solved by just actually taking two paths. So I just start with two gyroscopes. With one, I make one path, and with the other another one, and they meet again at a certain point. And in total, that would be like a loop around where I just did two directions simultaneously instead of going once around. So I need two gyroscopes instead of one to do full loops, so to speak, in space-time. So that's the other difficulty. So yeah, so with that, that's the difficulty we can easily deal with. As I said, for the other one, we can either use the symmetry and then forget about the zero component, or we can also give the zero component the meaning, which we'll do a little bit later.
There is one question in chat.
Mm-hmm.
So is there any physical intuition on why we define the torsion and the curvature like we did in the beginning, or why do we call it curvature?
Yes, there is very much physical intuition to it, and that will actually be the topic very soon. I think maybe even, yeah, let's see, maybe I can even do it still today. I certainly plan to explain the physical meaning of curvature. That's actually an important thing. Yeah, I think I could just do it in the next lesson. I anyway should do it, and maybe it's a good time to do it. I will not do the torsion today. So as I said, to understand the geometric or physical meaning of the torsion is, okay, that's actually also well possible, but it's easier to do it once we have introduced so-called normal coordinates. So for that, I will wait a little bit, but for the curvature, that's just the next thing to come. So just bear with me for another half an hour and you will see the answer of that. At least for the geometry. Then for space-time, it's analogous.
So I also have a question.
Mm-hmm. Yes, please.
So you mentioned that, and we've seen that the torsion and curvature, you can get the expression for these two from the gammas that we defined.
Yes.
But does this sort of go the other way? If you have a given torsion and given curvature, can we get the expressions for the gammas, or is there more information encoded in the gammas that are not in the curvature and torsion?
Okay, yes, I see. So I think yeah, I have to think about it, to be honest, because normally I think of it in the following way. If we have the covariant derivative, then definitely we can extract everything, because the covariant derivative immediately gets leads us to the gammas. Now, okay, the question is whether the curvature and torsion is enough. You see, the reason why I cannot give you an immediate answer is there will be one other ingredient we will learn about. Namely, we will later define the connection, the affine connection in a particular way connected to a metric. But this is additional information. So normally we also know that the whole thing comes from a metric. And this gives us more constraints. And under these constraints, such things are possible. Now, I'm not sure without them, but let me check that and come back to you later, whether we can already at this point, with the structure we have introduced so far, from the curvature and torsion, get the gamma symbols.
All right, thank you.
Okay, are there more questions? Otherwise, I think it's exactly time to start. So if there are no more questions, that would have been perfect timing for me to start. But of course, I'm also happy to take more questions if there are any. But thanks for the questions in general. So I think it's nice to have some interaction, at least in the break, and also, of course, during the lecture. By the way, before I start, let me just say a few other general things. So you have probably, or hopefully already seen my email regarding the exercise classes. And we will, from now on, have all exercise classes purely online. The reason is obviously the current pandemic, but actually I hope that it will also make the exercise classes more accessible to those who are not able to physically be present for other reasons, because we have now many students from actually the University of Basel and also a few from EPFL, as I was told. And they are, of course, very welcome to also log into these Zoom meetings now of the exercises and attend them. So these are open to everyone that is part of the course according to the Moodle page. So you're really very welcome to attend any of those. And if so far you didn't have the opportunity to do because there was an overlap, please use now this possibility. There are several time slots, so you can see all that information on our webpage on Thursday and on Friday. And I hope that at least one of the time slots suits you. I would also, again, really want to encourage you to do the exercises. For example, the upcoming exercise sheet, which I will put online tomorrow, will involve calculations of all these objects that you have now seen, the gamma symbols, the curvature, and so on, for really concrete things. Like you can even start with something simple. Let's say we just take the plane, the two-dimensional plane, and ask ourselves, what are the gamma symbols there? Of course, the gamma symbols will depend on the coordinate systems you choose. And if you choose a Cartesian coordinate system, then the gamma symbols will all be zero, because in Cartesian coordinates, and that's essentially what it means, that it's really a flat and nice coordinate system, is that when you take the derivative in one direction, the partial derivative, you don't have to take care of the fact that the coordinate lines themselves are somehow bent and so on. But if you go, for example, to polar coordinates, this is already no longer the case. And to see that explicitly is actually very instructive. And you can do that in the exercises. So that's why I really recommend them. And then you can continue and go to, for example, the sphere and ask yourself, how do we now, in this concrete example, calculate these gamma symbols? How do we calculate them in different coordinates? Do these coordinate transformations really give us the right answers and so on? And again, I think this is extremely useful to do, even though it's a kind of mechanical thing, but to do it once at least gives some insights beyond the pure mechanics of doing it. So I think it's really an excellent point in time also to start doing exercises if you haven't done so far, and attend the corresponding tutorials. Let me also use the opportunity to make you aware of the question and answer session that we have now installed, which will take place usually on Tuesdays before the lecture. And for that, I would ask you, if you have questions, just to submit the question on the Moodle page so that the teaching assistant can prepare herself for the question and answer session, and then give you really an informed answer or explanation about whatever you would like to know. So this is a good opportunity if something comes up apart from the tutorials, to ask and get answers. But as I said, it would really be helpful if you submit the questions before. Otherwise, it's probably not possible to give you a satisfactory answer for general questions. Okay, so that was just a small. I think there were questions about when does it start. So Dixina, can you maybe briefly tell us when the Q&A session starts? Because you are the organizer of that one. It's at 2, I see in the chat. Okay, it starts at 2. And the Zoom link is on the Moodle page. Okay. Now, I think, yeah, we have now seen the curvature. We have seen the curvature components in coordinates. And an additional thing I really need to show to you, although you will probably at this point not really see why it's useful, but we have to do it for later use, is to note certain properties that the curvature has. And one of the properties which is obvious, which I already mentioned, is the antisymmetry in the last 2 arguments. So what I mean by that, obviously, is just in components, that if you have an expression like that, then it's equal to Ri, J, and M with the last 2 arguments flipped. And Okay, I don't think I have to explain that more. Just look at this definition and you see that immediately. The second thing,
You're
yes?
not sharing the screen.
Sorry? Does the screen sharing not work? Or?
Yes.
Aha, that's strange because on my computer I see it.
For me, it works. I see everything moving.
Aha. Okay, I think most people see it, so maybe it's a local problem. So I don't see any. So if anyone else doesn't see it, maybe write that now on the.
And now it's working.
Okay, good. Okay. So, and the second property is a property that should hold if the torsion vanishes. So if the torsion vanishes, and this is of course the relevant case for GR, we have something that is called the first Bianchi identity. Just abbreviate that here. First Bianchi identity, which says that the antisymmetrization of the last three arguments, which in components means this, so now you know that the square bracket is the antisymmetrization bracket, that this antisymmetrization is equal to 0. So, okay. Of course, I think I don't need to write it out. It's just all three combinations with the antisymmetrization. Maybe, okay, what I could do is to write something non-trivial, something that combines it with the previous thing. So if you already know that it's antisymmetric in the last two arguments, then, of course, I don't need to write the permutations of the last two arguments twice. So I could just, for example, say, if I write IJMN, this, of course, already includes also the term where n and n is flipped. Or I could equally well write it with a minus because it's just equal. So in other words, instead of writing all 6 terms by using this, I can just only write 3 terms, which are the 3 cyclic permutations. So in this case, MNJ plus RINJM. That's not yet the Bianchi identity. The Bianchi identity tells us, that's just the rewriting of this. The Bianchi identity tells us that this is 0. That's the Bianchi identity. Now, how can you see that? Let me just sketch the proof. It's really just an almost trivial verification, and I want to leave it to you if you want to do it in detail. But what you can do is to just write things out in terms of the gamma symbols. And of course, that would take some time if I did it completely, because there are lots of gamma symbols to write. But if you remember one gamma symbol that appears here, let me here scroll on the right page. So here I have the first term that just coincides with what we have defined here. So there's one gamma symbol of that form here. And there's also a minus. Let me maybe write it for this one. Gamma I J M, N. And there are, of course, more. There are the products, which I now omit just because I don't want to show the proof, but only sketch it. So there are, of course, also the other ones, but for the other ones, I can proceed in a similar way. If I, for example, take the gamma symbols of that term, then I just have the cyclically permuted ones. So I take only the derivative, the gamma symbols for which I apply the derivative, and I don't write the other ones. And then for the third term, I have something like gamma I, and now I think NM, comma J minus gamma I N J, comma M. And now what you can observe here already is that there are always two that appear with the opposite sign, if we assume that we are torsion free. So for example, if I look at this one, then this is essentially identical to, I think, that one, if I have symmetry in the first two low, or in the lower indices of the gamma symbols. And of course, I have this symmetry if I'm torsion free. So this thing and this thing cancel. And then the same is true for the others. So for example, let's say this one here cancels with one with mj here. It also has the opposite sign. And then this one here cancels with that one here. And the same is true for the other terms, which I now didn't treat, the ones here which appear in the product. Because you see, whenever I have one with a derivative jm, I also have one here in the sum appearing with jm. And so the same symmetrization argument that I just did holds for those symbols. It's just a matter of writing it down. But I think I will save that time to do something more important, namely to show you the geometric meaning of all these. Now, there's a third property. If the torsion vanishes again, so again, when we are in physical space-time, for example, there is also a second Bianchi identity. I guess you could have guessed that there must be a second, otherwise there wouldn't be a first. So, what does it say? It says that if I take the anti-symmetrization bracket of mn and I take the covariant derivative in direction k. So this is now about not the curvature itself, but the derivative of the curvature, then this is also zero. This proof we have to move to later. It's something that I think would be very tedious to do now, but it's much easier to do once we have introduced a new concept, namely so-called normal coordinates. Normal coordinates will be coordinates in which, at least at one point, the gamma symbols disappear. And if the gamma symbols disappear, this of course makes all these covariant derivatives just partial derivatives, and things become much easier. And then you can see. I mean, this is not trivial. If the gamma symbols disappear at one point, it doesn't mean they appear everywhere. So the derivatives of the gamma symbols will not disappear. But of course, if the gamma symbols disappear, then we already have an advantage, because whenever there's no derivative involved, we can just write the zero. But for that, as I said, we will have to first show that there are coordinates always in which the gamma symbols disappear, if we are in a torsion-free manifold. So that's for later. But it's probably useful to have here just a summary of all these properties for once. I think that almost finishes now the discussion of the curvature, except maybe for the most important part, namely for its meaning. And that is important enough that I devote to it a separate chapter. This will be a new chapter also in the lecture notes, which will be there in an updated version. It's not yet on Moodle, but I'm about to finish this new chapter. And this chapter essentially tells you how you should think of curvature and how this whole thing now connects back to the experiment I've shown with the globe. So you remember I had this arrow where I moved to the south and to the east, and we saw that the arrow will end up in different directions depending on the paths we take. And I told you that we want to make that quantitative. Now we have all the tools to make this quantitative, and the answer, as we will see, will be that the curvature is the answer to exactly that question. So the curvature tells us how much this arrow will deviate if we take different paths. So now we are really in a position to actually calculate these things. And that's maybe another reason why you should go to the exercise classes, because there you will look at the sphere. And so this very specific example with walking with an arrow around in the world, then can be, I mean, you will see that we can now quite easily calculate that. Because if you don't have all these tools, it would be generally relatively hard question to answer how these things behave if you take arbitrary paths. But with these tools, that's now all quite generic. And of course, the nice thing is you can do it for arbitrary curved surfaces, not only the sphere. So to understand it, it's actually good to, again, look at the case where we have a coordinate representation. So we look at a coordinate map. You remember from the beginning of the course that we always had on the left-hand side the manifold. So think of it as the real space, the globe, the sphere, or space-time. And on the right-hand side, we have a coordinate system. And now if we look at the loop on the manifold, this will, of course, also be a loop in the coordinate system. But here I want to go backwards. I want to say, let's define a loop via the coordinate system. So let's take two coordinates, xm and xn. And let's look at a loop which in the coordinate representation just corresponds first to a straight line up to, let's say, certain value for xm, which I call u. So that's just when xm is equal to u. Then I go into the direction of xn until my xn coordinate takes the value v, which is again an arbitrary value. So I go in this direction, then in this one, and then I move here onto the left-hand side, and again down, back home, so to speak. So I'm here again where I started, and I think when I talked or presented the arrow, I ended up in a different place, but I could, of course, also have made a loop. I could have walked to the south, then to the east, somewhere to Malaysia, and then again to the North Pole, where I live, or where I started. And so I get a loop. And of course, in the manifold, this loop may now look more complicated. So it's something like this. It's now no longer rectangular because the manifold may be curved. Now let's take a vector at the starting point. So this blue point corresponds to the starting point, and I just draw it. Of course, the vector is not an element of the manifold, but the vector is an element of the tangent space. But let me nevertheless draw it like that. Probably understand what I mean with it. Here would be the transported vector. So I somehow transport it along the one direction, and I will just in a minute define this symbol, tau 1, just means that I transport it by an amount u into the one direction. So that's the new vector. And then I continue with that. I get somewhere here and then here. And at the end, I transport it back home, but it's of course not guaranteed that the vector will still point in the same direction. So generally I get some vector set tilde, which is again a vector at P, but potentially a vector pointing in another direction. We already know from our considerations that it will generally point in a different direction. And the question is, how much different will it be depending on U and V? Now we need to make this a bit more formal. That is just a drawing. So we have a transport of the vector, and I will just indicate the transport in the direction I. So this is defined as the transport in the direction where I increase just the i's coordinate by an amount of s. So the argument tells me how much do I increase the thing. And I take an arbitrary vector at an arbitrary point. So let's say it's some point q. Of course, I will at the end apply it to this vector and then to the transported one and so on. But let's suppose you have an arbitrary vector v at an arbitrary point q. Then this vector will be transported to a vector which is given by tau gamma I. This is an object already defined. So it has almost the same notation, but this is now a tau with a little gamma below. Whereas this tau only has an I. So that's a more general thing. This applies to any vector at any point, and this tau here was defined by taking a vector I'm sorry, this should be a Q here at the end. It takes a vector somewhere on the curve, namely at the point where the curve parameter is 0, and transport it to the point where the curve parameter is S. But now I want to be able to transport arbitrary points Q. So that's why I define a tau, which acts on all points, and I make the curve dependent on Q. So what I define here is with gamma I being an integral curve of the vector field that is coordinate induced. So coordinate induced vector field is d to the dxi through Q. Okay, that sounds a bit complicated, but it's actually just what the picture says. So maybe you should start reading this and say, if I have a vector VQ and want to apply this map to it, what I do, I take a curve, which I call gamma, which is an integral curve of d to the dxi. So it means it's corresponding to a curve where I just increase the I coordinates. So if I would be m, it would just be a curve which, like this, goes just into the right direction in the coordinate space, in the coordinate representation. And now I parallelly transport the initial vector along this curve. So it really means I take this vector and transport it to here if I start from here. That's what this tau does. But the tau is now defined for arbitrary direction. So I indicates the direction and S indicates how much. Now let's apply this to our vector set. And I start here writing from the right-hand side, because as you know, we apply maps from the right to left. So what I do is, now I kind of formally, I put this picture into formulas. So I take the vector set P, apply a shift in the direction m, so tau m, by an amount u. And then next, I apply a shift into the direction n by an amount v. Then I apply a shift again in the direction m by an amount minus u. So I go back here, that's this part. And then finally, I apply a shift again in the direction n by an amount of minus v. And this whole object that I now get is, I call set tilde. So set tilde, it's of course still an object at P, because I started at P and I did all these transformations. So P, okay, I forgot to write down what P is. P is this particular, okay, it's probably obvious from the picture because I wrote set P. P is the point where I start. This move here can move anything. So it can also move stuff that is already there. But P is the point where I stop. So I need to remember later that, of course, this whole thing depends on how much I moved it. So the whole thing will depend on U and V. For example, if U and P are both 0, then of course I don't move the vector at all, and set tilde P will just be equal to set tilde. So actually, I'm more interested in the difference between the two. So let's define a vector delta set P of U and V. And okay, it's just the difference. So I'll just write it like this. That's now the interesting object. So that object clearly has a geometric meaning. Just the meaning I just indicated before or described to you. And if you can now express this object with the quantities we have introduced, with curvature, for example, which we will be able to do, then we have established the meaning of curvature. So the meaning of curvature will essentially be that it corresponds to that in a certain way. So in which way we will have to figure out. So actually it turns out it will depend on the curvature in a rather complicated way. I would have to integrate. But if I only look at things to first order, then it's quite simple. So think of this loop as being a quite small loop. So I just walk here in my office a little loop. Of course, for the Earth surface, that's a really tiny loop. And of course, then I only have a tiny delta, but this delta already gives me local information about the curvature. So you should think of u and v being relatively small. Or mathematically speaking, what we do, we look at the Taylor expansion in u and v and look at only the first non-trivial term. And so, of course, that means mathematically that for small enough u and v, we are arbitrarily precise. Okay, so what's the Taylor expansion of this in u and v? So, okay, I mean, you probably know what the Taylor expansion is, but we need to actually carry it out. So we expand around 0. And so, okay, to 0th order, we just have this thing. Then to first order, we have d to the du. Okay, I write it maybe not as a partial derivative because the partial derivatives are now reserved for vectors. So this is just really a derivative to the u of the function u0. And then, of course, yes, sorry?
There's one question, Chad.
Yes.
One guy didn't understood the induction behind why ZP tilde not equal to ZP.
Aha, okay, yes. Let me come back to that. So the set tilde is defined as this transport. So what it means is, if you remember the globe example, the set P, okay, unfortunately I don't have my globe here any longer, but let's suppose there was here a sphere. Now I take set P as the initial vector as I stand on the North Pole. I move down to the equator, then I move towards the east, towards India, so the pointer now points downwards, and then I move back up onto the North Pole. And now you see the pen now points in the left direction, but I started like that. So the set P would have been this, the set tilde is now the end position. I hope that answers the question, and if not, just then feel free to ask again. Okay, so in first order we have this. In U, and of course we also have a first order term in V.
There is one more question, please.
Yes, please.
So ZP tilde is not necessarily in the same tangent space as ZP. If so, to what vector space is delta ZP belong to?
No, it is, I mean, by construction. Okay, that's important indeed. So thanks for the question. But I really want, I mean, indeed, I can only take this difference here if they are in the same tangent space. So they should really be at the same P. And so I need to really make sure that Z tilde is in the same tangent space. How do I achieve that? I just define the loop here in the coordinates. If you look here on the slide here, I defined the loop in the coordinates. And you see what the loop does? It's really taking a vector first, around this loop. And if I now apply, for example, this T mu, I'm guaranteed that this vector here, the one after applying the first tau, is a vector in the tangent space corresponding to the point I mark here. Now the next thing, if I look at this will really be a vector in the tangent space corresponding to the point in the manifold whose chart representation is here, and the next one here. And the final thing, this here, because I really transported it around, will again be a vector here. So it's by definition, I close the loop, and therefore the finally transported vector will be at the same point as the initial one. But I need that, indeed. Okay, then the third, okay, then I have, of course, a second order. So, for example, d to the d u squared, delta zp u0, and then times u squared. And then I also have a term d squared to the dv squared. Actually, there should be a 1/2, I guess, in the Taylor expansion. So there's a 1/2 in front of these square terms because I'm already in second order. And here is delta 0v. There's also a mixed term, and this is actually the only term that will be interesting, as I will just explain. So I take the derivative in both directions of u, v. And of course, what I forgot to write here, but should, of course, you know that probably is when I take the Taylor expansion, I should always evaluate around the point around which I expand. So I indicate this with these blue vertical lines that I want to evaluate this at u equals 0 at the point where I draw the line. So this is v equals 0. And I see that space is here a bit tight. So let me move this whole thing a little bit. There should also be at the end here a times v. And here should be a v squared, and here should be a u times v. And again, that thing has to be evaluated at u equals 0 and v equals 0. Okay, so that's the Taylor expansion. Of course, there are more terms, plus higher order. So the next terms involve something to the power of 3, at least. Now I will not write down things, but just argue in words why all the terms here will disappear. So why do they disappear? The reason is simply that in all these terms, we have always at least one of the arguments which is 0. So you see here the v is 0, here the u is 0, even before I take the derivative. I mean, because of course I can put the v equals 0 before I take the derivative with respect to u. Now look at this definition in the case where one of the arguments is 0. Let's, for example, make v equal to 0. So when v is equal to 0, this is just the identity map, and this is also the identity map. It just means I don't move. So what I do, I move into the u direction, do nothing, and move back. So it would just be a loop, which is essentially has no area. I move here, this, like this, and I move back. And of course, if I move forth and back exactly along the same path, then the directions don't change. That was also a property, by the way, of the parallel transport. That parallel transport is composable. And of course, the composition of this curve with that curve just gives the trivial curve that starts at the same point where it ends. And in this case, I have the identity. And so the derivative of the identity just gives 0. So all these terms vanish here because the derivatives are 0. And this is anyway 0 because this corresponds to just no path at all. And so if I have no path at all, then z tilde is just equal to z. And therefore the difference is 0. But this argument doesn't apply to this thing here. So here I really have to evaluate the term and actually do a little calculation. And actually the calculation here is not too difficult. So we are quite lucky that we can do this without a larger effort. But as a preparation for this small calculation, I need to say something else. And I just say that as a little note. The note is the following. If I take the derivative of this function tau, the parallel transport, of a vector v, and now I will just look at it for a whole vector field. So remember this tau map here, I defined what it does if it acts on a vector at the position q. But this is, okay, I didn't maybe say that, but maybe I said it, but didn't write it. This should really be true for all q. So I can take a vector at any arbitrary point on the manifold, and it will be, or at least in the chart. Of course, this we only need it in the chart domain. So I can take an arbitrary point q or a vector on a point q in the domain u of the chart and transport it in this direction. So when I write here v, then what I mean is it's just a vector field that I can transport up with this map. Now I can still, once I've taken the derivative to s, so taking the derivative with respect to s just means I'm interested in knowing how does the vector change as I start transporting it? And this immediately reminds you probably of the covariant derivative. So essentially what I want to argue is that this here is more or less the covariant derivative, but it will actually be minus the covariant derivative. And to see that minus sign, I need to be a bit careful, or I need to explain to you more precisely what we do here. So we take the derivative to s and are interested at the point where s is 0. So just when we start moving the vector, we start from a point Q and start moving it, how does it change? And then we evaluate this at a certain point P. And here it's actually important that I don't first evaluate it at the point P, because if I take the derivative after evaluating this at P, this will be a vector at a different point. And I cannot take differences between vectors at different points. Okay, that may not, this comment may not have been clear to everyone, but just this will become clear in a minute. So let me write down explicitly what this derivative means. We have done that in the past already. So what the derivative means is I just take essentially the function, apply it, and take it minus the function evaluated at 0, which is just the identity map. So tau with the value 0 is the identity, and apply this difference to v, but normalize it by s. So that's just essentially the definition of the derivative. But you see, it's important here that I didn't put here the vector at the point P in, because then I would have here a vector at the transported point, a little bit away from P, and here I would just still have the vector P, and I cannot subtract it. But if I write it like that, I don't run into this problem. So that's all well defined. So I still have to evaluate the whole thing at the point P. And now I just do something that looks maybe quite useless, but it helps us make connecting it to the covariant derivative. I write this whole thing by multiplying it with, on both sides of this difference, by the inverse of tau. And of course, what we know is that if I take the limes of s to 0 of tau I inverse, so what's the inverse of tau? It's just moving in the minus s direction. But if I look at this in the limit where s goes to 0, I also get the identity. So I can always multiply everything by this, because that's just multiplying with the identity. So what I get is the following. Here I will just get the identity in the first term, because obviously multiplying this with its inverse just gives the identity. But the identity multiplied with the inverse gives just, of course, this inverse of tau. So I've just moved essentially the tau to the other side. That's the only thing what I achieved here. And then again, I evaluate this at the point P at the end. So this sounds, as I said, not very useful, but now you will see why it's useful in this step here. So instead of now writing the identity minus this applied to V, I just apply the identity. So I can also write here, this is V. And because it's anyway evaluated at P, I can write VP. And then I put here tau gamma. Now I put in the definition of tau. Tau means I really transport along the curve gamma. That was this thing here that I'm now putting in. And actually, because I have a minus s, this changes the order here. So I'm essentially going in the opposite direction. And you know, if I change here the arguments, that's the transport in the opposite direction. So I can just write it with this inverse order of arguments. And now here I need to put a v, but because I evaluate this thing at the point P, I need to make sure that this is really a vector at point P. But for this to be a vector at point P, the argument that goes into the transport needs to be a vector at gamma of s. Because if I transport the vector at gamma of s back by minus s via this tau, I will end up with a vector at P. So let me write this briefly, just as a note, so that you see here the point I want to make. This is an element of TPM. And so I can actually subtract it. So this is again divided by S. Okay, now, if you look at this expression, this is now really like the covariant derivative, except for the order of things. So in the covariant derivative, this VP that appears here at the beginning is the second thing in the difference. So it's just minus the covariant derivative. So it's the covariant derivative along the curve, but the curve gamma goes along the coordinate xi by definition. So it's this evaluated at P. So in other words, what I've established here is that this the derivative of such a tau map, of such a parallel transport, is really just minus the covariant derivative. And now we can very easily, okay, I know it's already time to stop, but let me make this last calculation. It will probably take another 2 or 3 minutes, but certainly not more. The only thing, namely, we need to do is to evaluate this thing here. Delta ZP. Actually, instead of delta ZP, I could just write Z tilde P, because delta ZP and Z tilde P are just differ by ZP itself, but ZP is a constant, so if I take the derivative, this doesn't change. Okay, anyway, I think it's not useful. Let me nevertheless go back to this, because at the end, we need this to be evaluated, but it would be the same. Now I just do it in the order that I first take the derivative with respect to V and then with respect to U. So what's derivative with respect to V? Now we have to remind ourselves what the expression was. So this was the expression, and as I said, it's the same for Z tilde as for delta Z. So if you take the derivative of this with respect to V, we have to apply the product rule. We get a term from this V here, and we get a term from this V here. So the first we get is, therefore, the term from this is now exactly what we did here. So it's a derivative of this type. So it's a covariant derivative with a minus sign. But because there is already a minus here, the minus cancels. I will just get a derivative in the direction in which I'm going. So this was here the direction n of this tau. Tau went in the direction n. Then the other term is unharmed, the minus u term, and then I also have the tau u term. I didn't now write this term here, tau v, because v is set equal to 0, and then this is just the identity. But this was just the first part of the product rule. I also have to evaluate the second part of the product rule. The second part will give me, okay, maybe plus or minus, we have to leave this open. First, the tau n in the minus u direction, because this thing goes anyway away, t minus v, because v is equal to 0, and I'm not taking the derivative of that. So the first relevant term is this. Then the next one is this, to which I apply the derivative. Here I actually get a minus. So let me put the minus here, because it's a plus in the argument. So we get this minus here. Delta nabla e to the dx n, again go in the n direction in the v, and then the last term is a tau m of u. Now, okay, it's very easy now to conclude, because the derivative with respect to u of this term is 0, because these two terms just cancel. It's just a transport and then a transport in the opposite direction. So I can just forget this whole first term here. So this is just broken out. But I still have to take the derivative with respect to u of this term. And here again, I have to apply the product rule. But the product rule just tells me, if I first apply to the first u, I get a delta in the m direction, e to the dx m. And then I write the rest, e to the dx n. And the last term is just the identity because I set u to equal to 0. And then I have the opposite thing. I also get, if I don't take the derivative of this, I get a u equals 0. So this is again the identity. I start with this term, e to the dxn, and then the last thing gives the derivative d to the dxn. And then we are done. So I think I got the set at the end. So this whole thing is applied to set. Now we are essentially, now we are really done, because now you see this is just the expression for the curvature without the Lie bracket. But the Lie bracket is irrelevant because we have here a derivative in the direction of the coordinates, and you know that for the coordinates, the Lie bracket disappears. So essentially, this is just equal to minus r, and here, this is, if I leave this open, it's like a vector of d to the dx m d to the dxn. That's what it is by definition, essentially. So in other words, what we have found is that, if you now go back, the only term that survives is this one, but this term is exactly the curvature, and with the set put in as an argument. So in other words, and of course this whole thing, by the way, this term is still multiplied with u and v. So the statement we conclude at is the following. If we do a loop like this in direction u, in the m direction of the coordinate system, then by v in the n direction and then back, then the amount by which the vector has changed is given by u times v times this term, which is exactly the curvature applied, curvature applied to these directions. So we now understand what these arguments mean of the curvature. So this is the vector we want to kind of transport. That's the second argument to the curvature. That argument is in which direction we move first. This is the argument which tells me in which direction I move second. And then the curvature tells me what is the new vector, so to speak. Okay, so just for those who are still here, it may have been unclear why I put here this dot. So let me just maybe explain that. I could just put dxi, if you like, to this whole thing, to delta z u v. Or uv. And then this extracts the i's component. So then I would really have something like r minus r dxi set d to the dxn d to the dxn. So that was the meaning of the dot. So if I extract the i's component, I need to put in here an I. And of course, if I write it like this, then there's still the uv. So that's our result. So to first order, or to actually second order, we know that the i's component of the change of the vector is given by this expression, which is the curvature times u times v. Okay, so I think that's it for today. I'm sorry for actually the slight delay, or yeah, I think it's quite a lot over time. But at least we have arrived at a very interesting point. You should now have a clear understanding what curvature means. So these things, this R, I, J, M, N, really have a very direct meaning of how vectors change as you move along a loop. And that will, of course, be very useful for the further understanding of this lecture, where this object will be applied to space-time. Of course, in space-time, it's a bit harder to think about curvature, but you should always project it down to something you understand and think about surfaces, and then you understand the curvature, and then you can somehow think of space-time as just being the higher dimensional analog of that. And all these components of the curvature are needed because we can move in different directions, we can start with different vectors, and we can also ask about different components. So all these arguments really make sense now, I hope. Okay, that's it for today.
Sorry, can I ask
a nice evening, and hope to see you again on Thursday.